Hello and welcome student. So we will start our discussion today. So this is course number MA412 linear algebra, and this is a lecture number 5. Okay. And today we are going to learn one of the very important idea in linear algebra, and this is called linear transformation or linear maps. Okay, so let me write down the name properly. Linear transformation. Okay, so linear transformation, also sometimes we will call linear maps transformations. I mean both name also you will use. Okay, linear maps is easy to write down, it's small. Okay, so so what kind of map is this? Like for example, whenever we learn any structure, we learn some kind of maps which preserve the structure, right? You may have learned in group theory something called group isomorphism, right? Homomorphism, isomorphism, ring theory also. Ring homomorphism, ring isomorphism. Similarly, in linear algebra, in linear space, you have some kind of map which preserve the structure of the spaces. And these kind of maps are called linear maps, or linear transformation. So how to write down the definition? So suppose you have two vector spaces. So let um, so a map, maybe let me write down the symbol, say whatever. So if from two vector spaces, so V to W, so B and W may not be same, but they have to be over same field. So let me write down V over F, same field. So a map F from this V over F to W over F is said to be a linear map if what happens if this following holds. If number one, so if is kind of something called additive. Additive means what? F of x plus y equal to f of x plus f of y. This is true for every x and every vectors. F of y belongs to V. Okay, and if you see that f of x and f of y are element of W, so this operation here is inside V, and this operation here inside W. So I am using the both the same operation. Okay, but this is operation of vector space V, and after the operation you are in the right hand side you have operation of W. Okay, and number two, so this property is called additive property. Okay, what is number two? Number two is that whenever you evaluate at a point at a vector with some scalar multiplication, it is enough to first evaluate at the vector and then multiply by the scalar. Both are same. Okay, and this is also true for all C belongs to F and X belongs to V. Okay, so what does that mean? That means it doesn't matter whether you are first taking the image and then multiplying the constant, or you first taking the multiplying the constant and then take the image. Both are same. Okay, so if a map satisfy these two properties, then these kind of maps are called linear map. Okay, or linear transformation, whatever. Okay, so obviously there are so many properties Maybe we can start with some example first. So examples. The very basic example. So if you have okay, so let me start with this symbol I from V to V. That is defined by I of x equal to x, or like this kind of this maps is called the identity map. Okay, so identity map on any vector space is always linear map. Okay, and it is very simple to prove. You can easily check it. Similarly, there is another very simple map. It's called zero map. Let me write down this by this symbol theta. So this is what is this map is sends every element of x to 0. Okay, so this map is called zero map. So first one is called identity map, second one is called zero map. Okay, these maps are trivial maps. Okay, and these are all linear maps. Okay. Similarly, if you want to find out some things which are non-trivial, so if you take, for example, if from real line to real line, okay. So instead of I, which was identity, you can, so identity was taking element to the same element, right? But if you define something by an element multiplied by a constant, some constant of R, okay, for some C belongs to R. Then also this is a linear map, right? Because when C equal to 0, this becomes a zero map. When C equal to 1 is identity map. And when C not equal to 0 or 1, then also this is a linear map. We just prove it. These are simple maps, okay? Similarly, you can talk about the higher dimensional spaces also. So this is okay. So this simple map. So maybe R2 to R2. Let me give something. R2. I'm thinking R2 over R. Okay. This is also I'm thinking R over R. I can vector space. So R2 over R. So two-dimensional vector space. Okay. And so what does that mean? That means there will be a order pair. So choose x1, x2, and send it to something like. And there are so many such maps, right? So I am just giving you one example. Maybe this. Now check that this is also linear map. Okay. There are some nice linear maps also. Okay, for example, if you are in some vectors in R2, maybe x1 and x2, and you can do one thing. You can just take, you can just omit this y-axis and take this image of this on x-axis. This is x1 0, and these kind of maps are called projection maps. Okay. So this is kind of maps are called projection. This is projection on x-axis. Okay. Similarly, you can have projection on y-axis also. So this is 0, x2. So projections. These projection maps are also. The projection maps are also. Okay. So let me write down R2. You can say R2 to R also, R2 to R2 also, doesn't matter. Let me write down by these and say x1, x2, and the image is x1, 0. So this projection on this, maybe you can have another one is 0, x2. Okay, so these are also linear maps. And proof is very simple. Okay, so I am not writing. You can check this at home. Similarly, you have there's something called reflection map. So what is the reflection map? Reflection map is kind of, you have a point here which is a vector, say x1, x2, and you have to check what is the reflection with respect to x-axis, so that will be something like that here. Okay, so this will be x1 minus x2. Okay, so this map is called reflection map, and this is also linear. Reflection. Okay, so what is the definition? So if of x1 comma x2 going to x1 minus x2. So this is reflection on x-axis. Similarly, you can have reflection on y-axis also. So like this. Okay. So these are all linear map, and you have one more nice map. It's called rotation. So what is that? So what is the number? So 6, 7. Then so rotation by some angle. Say rotation by some angle theta. Okay. What is that map? So we have okay, and you choose a vector. Maybe the angle is alpha originally. x1, x2. Then you do this reflection by theta. Okay. This is a new vector. Okay. And you can easily check that this map is also that's why I'm giving this anti-clockwise rotation by theta. Okay, you can give clockwise also, no problem. So I'm just taking anti-clockwise. Okay, so the image, what will the image of this will go to from this point to this point. Okay, from here to here. Now we can easily calculate what is that point, no problem. But this is okay. So you give rotation by this, and for origin of the 0 rotation by theta will be same point, right? Because this is origin will never rotate. Origin is kind of center, is kind of always well, whatever rotation you give, this is that this point will never move, right? So under that map 0, that theta goes 0 goes to 0 also. That will be one more property that we are going to show you after that. Okay. So how do you check this map? Is this map is a linear map. So this is simple. So if you give rotation by theta and this, and then it will be again rotation by theta 1 plus theta 2. And what will be image actually? So it is simple to find out image. For example, suppose the length of this vector is r. So r is some kind of x1 square plus x2 square. Okay, this is r, and this is the alpha. Then we can talk about what is x1, x2. So x1 will be r cos alpha. This is simple geometry you have learned in your schools. Similarly, x2 will be r sin alpha. Okay, so this is r cos alpha. This much is r sin alpha. Okay, and by that you can also consider the vector. So this is kind of polar and Cartesian you can think about. Okay, so then this is polar r cos the alpha, polar coordinates. Now so with the help of that, what will be the image? So image will be, you just let me write down f theta, which is rotation by theta. Okay, and what will the image? So you are sending, so r will be same, right? When you rotate that vector, the length will not change. Okay, only the angle will be changed. So what will be the angle? So originally the angle was alpha. So the vectors are cos alpha, r sin alpha, right? This was the coordinate of the vectors. So after rotation it will be r, that angle become alpha plus theta. So r sin alpha plus theta. Here will be r sin alpha plus theta, right? Now this is simple formula to find out this cosine formula. So it will be r cos alpha cos theta minus r sin alpha sin theta, right? Similarly here r sin alpha cos theta plus r cos alpha sin theta. So this will be the coordinate of the vectors after the rotation by theta. But we already know that r cos alpha is nothing but x1 and r sin alpha is x2. So this will be x1 cosine alpha cosine theta minus x2 sin theta. Okay, first coordinate. The same coordinate will be x1 cos theta. No, x1, it is x1, right? x1 sin theta and plus x2 cos theta. This will be coordinate. Okay, this you can think about multiplying by a matrix and a vector. So x1, x2. What is the matrix? Can you find out? So this is simple, right? So you multiply by matrix, which is cosine theta minus sin theta, and then sin theta cos theta. This is the matrix, right? So you can write down this is kind of a rotation matrix. Okay. So there are so many ways you can see, so many examples are there. Okay, so one can write down thousands of examples. Okay, so now there are few basic properties so that easily one can prove it. So let us do some properties. So what are the first basic property one should always remember that the image of zero vector will be always zero. So what does that mean? That means, so if you have a linear map from V to W, this is given to you, then the zero vector of V that map to the zero vector of W. Okay. So remember when we are not writing V and W, we should always assume that this is vector of V, this is vector of W. But in general, we don't write down this. We just write down f of 0 equal to f of 0 without don't making any ambiguity. Okay, but it's actually 0 vector of V, 0 vector of W. And the proof is simple. So you need to use the first property. This first property tells you that f of 0 V plus f of 0 V, that is nothing but f of 0 V plus f of f of 0 V, right? The first property of linear maps. But here, when you add two zero vectors, you know that this is always a vector. So left hand side will be f of 0 V and right hand side will be f of 0 V plus f of this zero vector of V. But again here inside, when we talk about f of 0 V, you are inside W, so you can add zero vector of W here, so that doesn't matter, it will never change. Now you can apply the cancellation property, so this will get cancelled, and hence you will have f of image of zero vector of V is nothing but the image of zero vector of W. Okay, so this is a simple property, and property number 2, which is very important, which tells you that the two properties 1 and 2 can be written as so f is from this to this linear if and only if and only means both the necessary and sufficient condition. Okay, if and only if of cx plus y equal to c times fx plus f of y. That is true for all c belongs to f, all c belongs to f, and xy belongs to that vector space B. Okay, this is if and only condition. And super means there are two ways, right? So one part is obvious, right? So if f is linear, this is obvious because this is coming from first property addition and is coming from second property, right? So one part is obvious, one is trivial actually. Now converse part is conversely if f of cx plus y equal to c f of x plus f of y for all c belongs to f and xy comma y belongs to v, then what happens? Then you can choose particular c equal to 1, right? Because c is a field inside the field and 1 is the identity inside the field, right? Then for c equal to 1, what happens? C equal to 1, you have the first property f of c x plus y equal to f of x plus y. Okay. Okay, and for second property, yeah. So this first property, second property was if you multiply by constant, then that will be also same. So okay. So now you have this property. For you choose that y equal to 0 vector. For this is true for every vector, right? So second property, you just choose y equal to 0 vectors. Okay, 0 vector of v. Then what happens? Then you get a z property number 2. So that will tell you that f of c of x, nothing but c times f of x. Yeah, so sometimes it is also so this is the proof, but sometimes people also, instead of that, if people also write down c1 c2, write down like c1 x c1 x plus c2 y equal to c1 fx plus c2 f of y. And this is also equivalent to this definition. So whatever you choose, you can write down. Okay. And now obviously and this next property will be again similar. So if you choose the negative vectors, so x minus y, and that automatically will be f of x minus f of y. So this you can think about. So this you can think about f of x plus minus 1 times y, constant, right? And the first step will be property 1, that it gives you f of x plus f of minus 1 times y, and then property 2 gives you f of x minus 1 multiply outside, so minus 1 times f of y. So right, so f of x minus f of y, right? So this property are very simple. And also what happens if you multiply by scalar and add by finally many times, and that is also similar. So f of summation something, say ci xi I equal to 1 to n, that will be summation of ci into f of xi I equal to 1 to n, and that is for all. I mean, this ci is an element of a field, and this vectors fi xi is an element of the vector space V. Okay. So these properties are very simple. You can easily check. And here you need induction, the proof by mathematical induction. Okay. So now once we know what are that linear transformation, their properties, their maps, so let us now define a very interesting subspace, a very interesting set. Let me see first what is their set, and then we will define their properties also. Definition. So we have, say, let f from V to W be a linear map. Okay, so we say the kernel. Okay, so be a linear map. The kernel so sometimes it is also called null space, or you can write down the null space of f is defined by how to define this null space. Write down that car, this is the symbol we will use, car of f, or you can write down n for null space of f. It's better to write down kernel in that symbol. So this is what? This is collection of all those vectors. You choose all the vectors, say v inside the domain, such that the image are 0 inside and the codomain. So such that what? Such that f of v is actually 0 vector. So 0 vector means 0 vector inside W. Okay, we collect all such things, and then we call this is the kernel of this maps. Similarly, we define something called the image or range. The image or range of f is defined by so people also write down image of f, or some people write down range. Let me write down this symbol, range of f, and this is what? This is collection of all the vectors f of v, such that v is element of that vector space v. Okay, so these two sets, special sets we define, and now you note that the first one is actually sitting inside v, and second one is sitting inside w. Okay, so they are subset, that is clear. Okay, now question is that whether they are special kind of subset, or these are only a subset, right? Okay, so now the answer to this question is that they are not any special subset. They are actually subspaces. Okay, now recall what is subspace. Subspace means they itself is a vector space. Okay, and also you can prove subspace by other property like that original zero of the vector is also inside the subspace. Okay, and the closed under addition, closed under right scalar multiplication. So you have the property to prove something is subspace. So this is homework. So homework. Check that. Both kernel. The kernel is a subspace of um, V and image or range whatever. So I can write down this symbol also image of this is subspace of W. Okay, so this is homework. So so you know how to check subspaces. Either you can use the property of subspaces is a vector space, or you have equivalent condition that 0 belongs to this, and also is closed under addition and closed under scalar multiplication, right? Okay, so with the help of this definition, we can have there are some important theorems, and that theorem is our final discussion today, and this theorem is called the Rank-Nullity Theorem. Okay, by this we will finish our today's discussion. So this very important theorem is called Rank-Nullity Theorem. Okay. Now of the natural question, what do you mean by rank? What do you mean by nullity? Right? This is a natural question. So let me first define that things, and then I will tell you what is that. So suppose we have two vector spaces with the same over the same field, and we have a linear map. So if a linear map from V over F to W over F. Okay. Be a linear map, then this theorem tells you that rank of or nullity, whatever you first write down, no problem, nullity of F plus this rank of F. This is nothing but dimension of the vector space V. So this is the symbol dimension V. Okay. So obviously first we need to understand what is the meaning of rank and nullity, and this is also define it. So what is the nullity? So nullity of F is nothing but the dimension of the kernel of F. So because kernel of F is also a vector space, so it has a dimension. Okay, so I'm assuming for example I'm assuming finite dimensional vector space first. Okay, because if like V is finite dimensional, I'm assuming that dimension of V finite. If dimension of V is infinite, then obviously then it has no meaning actually. So at least some nullity or rank will be infinite, right? It has no meaning. So I'm assuming it's finite, and hence kernel of that V, kernel of F is which is subspace of V is also finite dimensional, because subspace of finite dimensional vectors is also finite, and you can talk about the dimension here, and this will be dimension of the kernel of F. So that is my nullity, and similarly you can talk about dimension of rank, dimension of the range or image, and that is called the rank. So what is rank of F? So rank obviously is nothing but dimension of the image or range, whatever range of f. So that's right. So this is called rank-nullity, and if we add it up, then it will be dimension V. For the case of V finite dimensional. So if V is infinite dimensional, then obviously, so these theorems is. I mean, there is no meaning actually, no meaning of these theorems. Then you can say it will be right, because right hand side you have infinite, one of the left hand side will be infinite. So right. So it's not so much interesting. Okay, so what does that mean? So you have a like spaces V and W, and what you do, you just take that map and you see that something here. Something here. Okay, so this is your range, and you calculate what is the dimension of this space range. Okay, and also inside that zero is there. Now you see that inside that a full thing that map to zero. Okay, something like that. Okay. Now you see that those who map to zero and those which are actually mapped to things, these things. So it's kind of this dimension is kind of this dimension. If you add those things, this plus this, you will have full dimension. This is the intuitively you can think like that. Okay. Now what will be the proof? So how do you prove it? So to start with, say something dimension is n. So let me start. So let dimension of V is say n. Okay, and nullities or null space kernel, whatever you write down, nullity of f is k. Okay, so what does that mean? That means there will be k dimension subspace of V that maps to zero vector there. Okay, so obviously so you can choose a basis from this null space. So I choose it. So let the basis so V1, V2, say Vk be a basis of this kernel of f. Okay, the null space. Okay, and you know that, so these vectors, if v1, v2, vk are linearly independent vectors inside n, inside V, and dimension of V is n, which is so this k is less than or equal to n. Okay, so obviously the moment you have a linear independent vector, you can extend it to the basis. So as this is Vk is linearly independent. So I'm writing in short, but generally you should write down full name. Linearly independent set in V over F over the field F. So we extend it to a basis. A basis of B. Okay, say B, skip B, and this is kind of V1 up to Vk, and then Vk plus 1 to Vn. Okay, so this is the basis. Now obviously these generates V1 to Vk generates the kernel of f. Okay, now my claim is that this vector, whatever is remaining, these vectors, if you take the image, they will generate the range. Then you are done, because then dimension of range will be exactly n minus k, and if we add n minus k and k, you will have n, right? So what is our claim? If we choose so what should be the name of this thing? Maybe b1. So b1 is the image of this under the map. So f of v k plus 1 dot 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 f of vn is a basis of this range of f. This is our claim. Okay, so you have a basis. You start with the basis of this null space, and then extend it to the full basis of the vector space, and then we got and then you see that whatever element are there which are not a basis of that kernel, the images also forms a basis of the range space. Okay. Now to prove that this B1 is a basis, what you need to prove? So you need to prove two things. You need to prove that this is a spanning set and also linear independent set, right? Now to prove something is a spanning set, what you need to prove? Okay, so to prove something is a spanning set, what you need to prove? So you need to prove that the every element of the image is actually inside the span, right? Span of that, right? So how do you prove that? So let you choose the element, say W belongs to that image of or range of F. Okay. So what does that mean? That means there exists some V belongs to V such that f of v equal to w. This is the meaning that w is the element of the range. Okay. Now v is inside v, right? So again, if v is element of v, so v can be written as some ci vi I equal to 1 to n. Okay, for some constant ci, and vi is at the basis vectors, right? Okay, so we know one more thing. We know that f of v1 up to f of vk, their image are 0 actually, because they are basis of the null space, so the image will be 0, right? So this is we know. So when you write down this in terms of f of v and the property we just proved of linear maps, because okay, so yeah, this is linear map, we know that, right? So this property tells you that this is f of summation ci vi I equal to 1 to n, right? And that will give you summation ci f of vi I equal to 1 to n. But you know that till I equal to 1 to k, this is 0. So you ended up with summation ci f of vi and I equal to k plus 1 to n, right? So what does that mean? That means every vector can be written as a linear combination of element of b1. Okay, thus that's the span of the range of T is nothing but the span of v1, right? Because you can write down any vectors of range of f. What I am saying, range of f is written as element of b1, right? Okay, so this was simple thing done. So next part is what? Next part is you need to prove that the set B1 is actually linearly independent. So what does that mean? That means if you have some linear combination, non I mean if you start with some linear combinations, which is trivial, then that coefficient will be all zero, right? So you start with that. So let to show linear independence of P1, let so you start some alpha f of vi I equal to k plus 1 to n. This is 0 for some alpha is belongs to f. Okay, now if this is 0 for some alpha belongs to f, then we need to prove that these alpha are actually 0. Then we are done, right? All the alpha are 0. Now if this is 0, then we know that I mean obviously you can prove the property of linear transform tells you that this is nothing but f of summation alpha i's v i's I equal to k plus 1 to n. This is 0, right? We know that. This is the property of linear maps. F is linear, right? Now f of something is 0. What does that mean? That means this vector is an element of the kernel. So this means this in summation alpha i's v i's I equal to k plus 1 to n. This belongs to kernel of f. Okay, and you know that kernel is also actually generated by the basis of kernel is v1 up to vk. So what does that mean? That means you can so thus there exists, you can write down these vectors in terms of v1 to vk. So thus there exists some beta is belongs to if the field f such that what happened, such that these vectors summation alpha i's v i's I equal to k plus 1 to n can be written as summation beta i's v i's I equal to 1 to k, right? Because I equal to 1 to k, v i's are actually basis vectors of kernel of f, right? Now once you will have this thing, then you can do one thing, you can write down everything in terms of one place, and you can talk about that. So this implies what? This implies summation. This is what? This is beta is, right? So you take one side, so this minus beta is v i's I equal to 1 to k and plus summation alpha is v i's I equal to k plus 1 to n. This has to be equal to 0, right? But you know that v1, v2, vk, but that b is, what was the b, the original, the time, that basis of, so this where is that b? Yeah, so this b, see, this b, this is the basis of the vector space v. So v1, v2, vk, and v plus 1 to vn. So these vectors are linearly independent, right? Because this is a basis. So this v1 up to vk and then vn. So this is a basis, right, of v. So what does that mean? So if you have linear combination of linear vectors, that implies that all the coefficients are 0. So in particular alpha i's are 0 for all I equal to k plus 1 to n, right? So all those vectors are 0, and hence what does that mean? That means thus this vector t v k plus 1 sorry, f not t, what I meant to f of, okay, so what did I define it? Somewhere here, yeah, so f of vk plus 1 to vn, that is beta 1, so vn, So this beta 1 is actually is a basis. The basis for image or range, whatever you say, of f. Okay, image of the done. So this proves the theorem. Okay, so because this n minus k, this was dimension, another dimension was n, and hence and total dimension is the dimension of v. Okay, so this is a very important theorems, and maybe we'll do some applications to these theorems next day, and some more property that we are going to learn next day. Okay, so today I'm going to stop here now.